Hey everyone, we're moving on to the next chapter of Think Python. This one's kind of weird. This is chapter 12, text analysis and generation. Not something I would personally consider as like a good primer for computer science. And my wife is trying to distract me in the background with some weird dances that none of you will ever see, or, you know, you will die if you do, because I will kill you. No, I won't. That's a terrible thing, and this me starting the video like this is probably gonna get me demonetized. Not that I really care. So let's start reading this. This thing, gonna get into Markov generation, and this comes in like bigrams and n-grams and stuff, like some NLP stuff. I remember Markov chains like being like the cutting edge of NLP, or it used to be. Like many, like several decades ago at this point. This is not true anymore. Uh, Kind of a weird inclusion, in my opinion, as a chapter in this book, but I am still curious because I actually don't understand how Markov chains work really well. So this kind of be interesting for me. Okay, so at this point, we have covered Python's core data structures, lists, dictionaries, and tuples, and some algorithms that use them. In this chapter, we'll use them to explore text analysis and Markov generation. Text analysis is a way to describe the statistical relationships between the words in a document, like probability that one word is followed by another, and Markov generation is a way to generate new text with words and phrases similar to the original text. These algorithms are similar to parts of a large language model, which is the key component of a chatbot. Ooh, that's I wouldn't agree with that. I think modern language models are all transformer based, which is very far away from Markov chains. Conceptually similar idea, but still. Uh, we'll start by counting the number of times. One second. All right, I'm back. Sorry, I need to check up on something. That was important. But anyways, these algorithms, I was talking about how Markov chains aren't exactly what's used anymore in LLMs, but that's a different story. Conceptually, yeah, and I think it's a good thing to practice these older algorithms, because even if that specific algorithm didn't doesn't translate, doesn't mean others won't. It doesn't mean aspects of it won't, right? So it's always good to practice these. These algorithms are similar to parts of a large language model, which is the key component of a chatbot. We'll start by counting the number of times each word appears in a book. Then we'll look at pairs of words and make a list of the words that can follow each word. We'll make a simple version of a Markov generator, and as an exercise, you'll have the chance to make a more general version. Unique words. As a first step towards the text analysis, let's read the book, the strain. Okay, so we're downloading another book, and count the number of unique words. Instructions for downloading the book are in the notebook for this chapter. Boom. The version available from Project Gutenberg includes information about the book at the beginning and license information at the end. We'll use clean file from chapter 8 to remove this material and write a clean file that contains only the text of the book. Oops, that's not what I meant to do. Let me just hit run all. Version available from Project Gutenberg that contains only the text of the book. Def is special line. Return line dot strip starts with *** space. So that's kind of similar. Def clean file, reader and writer for line and reader if is special line break, for line and reader if is special line break. Writer dot write. Reader close, writer close. So the special line stuff is basically just the opening and the ending lines, right? So I believe if you call this once, it'll run through just the first line and break, and then it won't write anything essentially. and so we're just cleaning that file up. We'll use a for loop to read lines from the file and split to divide the lines into words. Then to keep the track of unique words, we'll store each word as a key in a dictionary. Unique words for line and open file name. Sequence equals line dot split for word in sequence. Unique words word equals 1. Length unique words. So yeah, we're making a dictionary and basically just creating a dictionary for every word that exists. And because it's a dictionary, we don't have to check. We can just do this assignment and it'll always only create one instance of that word because the word itself is the key. The length of the dictionary is the number of unique words, about 6,000 by this way of counting. But if you inspect them, we'll see that some are not valid words. For example, let's look at the longest word in unique words. We can use sorted to sort the words, passing the len function as a keyword argument so that the words are sorted by length. Yeah. And this is just looking at the last 5 elements. Superiors behold, coolness frightened, gentlemen something, pocket handkerchief. Anyways, slice index -5 selects the last 5 elements of the sorted list, which are the longest words. The list includes some legitimately long words like circumscription and some hyphenated words like chocolate color, but some of the longest words are actually 2 words separated by a dash. And other words include punctuation like periods, exclamation points, and quotation marks. So before we move on, let's deal with dashes and other punctuation. To identify the words in text, we need to deal with 2 issues. When a dash appears in a line, we should replace it with a space, then we use split. The words will be separated. After splitting the words, we can use strip to remove punctuation. To handle the issue, we can use the following function, which takes a string, replaces the dashes with spaces, splits the string, and returns the resulting list. Boom. That's pretty simple. Line dot replace dash space dot split. Notice that split line only replaces dashes, not hyphens. Here's an example. Split line, coolness frightened. Now to remove punctuation from the beginning and end of each word, we can use strip. But we need a list of characters that are considered punctuation. Characters in Python strings are in Unicode, which is an international standard used to represent letters in nearly every alphabet. Numbers, symbols, punctuation marks, and more. The Unicode data module provides a category function we can use to tell which characters are punctuation. Given a letter, it returns a string with information about what category the letter is in. Category LU. Category string of A is LU. The L means it is a letter, and the U means it is uppercase. The category string of period is PO. The P means it is punctuation. O means its subcategory is other. We can find punctuation marks in the book by checking the characters with categories that begin with P. The following loop stores the unique punctuation marks in a dictionary. If category dot starts with P, punc marks char equals 1. Yeah, so this is essentially doing the same thing as we did over here, except with punctuation and checking what category and figuring out what is appropriate punctuation by using the Unicode data module, which I don't know. Is that standard Python? Unicode data. Yeah, it is. Okay. We can find the punctuation marks in the book by checking for characters with categories that begin with P. The following loop stores blah. To make a list of punctuation marks, we can join the keys of the dictionary into a string. Punctuation equals, dot join punc marks, print punctuation. So this gives us all the unique punctuation. Now that we know which characters in the book are punctuation, we can write a function that takes a word, strips punctuation from the beginning and end, and converts it to lowercase, def clean word.strip punctuation.lower. Here's an example, clean _ word. Behold, which becomes just behold, lowercase and punctuation removed. Clean word pocket handkerchief becomes Now here's a loop that uses split line and clean word to identify the unique words in the book. Okay, so now we have all the unique words. With the stricter definition of the word, there are about 4,000 unique words. And we can confirm that the list of the longest words has been cleaned up. Sorted, unique words 2, key equals len, through -5. So just looking at this, we're seeing similar things as before, but we haven't done the split on the hyphen. Now let's see how many times each word is used. Word frequencies. The following loop computes the frequency of each unique word. Word counter for line in open file name, for word in split line, word equals clean word. If word not in word counter word equals 1, else word counter word plus equals 1. Yeah, so this is just a loop we've done before. It's just essentially counting each unique word and saving that info in a dict. The first time we see a word, we initialize its frequency to 1. If we see the same word again later, we increment its frequency. To see which words appear most often, we can use items to get the key value pairs from word counter and then sort them by the second element of the pair, which is the frequency. First, we'll define a function that selects the second element and then pass that as the key to sorted. Second element. Reverse equals true, and we can, here are 5 most frequent words. For word, comma, frequency in items, colon 5, print freq word separator / tab. 161 for the, 972, and obviously these are all words. In the next section, we'll encapsulate this loop in a function, and we'll use it to demonstrate a new feature, optional parameters. All right, optional parameters. We've used built-in functions that take optional parameters. For example, round takes an optional parameter called n digits that indicates how many decimal places to keep. But it's not just built-in functions. We can write functions with optional parameters too. For example, the following function takes 2 parameters, word counter and num. Boom. The second parameter looks like an assignment statement, but it's not. It's an optional parameter. If you call this function with one argument, num gets the default value, which is 5. So yeah, essentially, this is something we've talked about, I think on the second or third chapter, like several videos ago at this point. But essentially, like, this is another way to define arguments. You have a default argument, and when you have a default argument, then that parameter becomes optional, or that argument becomes optional. And because it's optional, A, doesn't need to be passed, and B, even when it is passed, you can pass it in as a keyword argument. If you have, for example, multiple optional parameters and there's only one you want to set, then you set it as a keyword argument, right? If you call this function with 2 arguments, the second argument gets assigned to num instead of the default value. Yeah, okay. Yeah, so this is basically the same loop we did earlier of printing out the most common words and just telling it how many words we want to print. In that case, we would say that the optional argument overrides the default value. If a function has both required and optional parameters, all of the required parameters have to come first, followed by the optional ones. That's not technically true. What is actually accurate is all positional arguments need to come before all keyword arguments, right? So you can actually give optional parameters as a positional argument, right? If it is in the order of, say, for example, you have 4 parameters, 2 are positional, 2 are keyword arguments, right? If you want to provide parameters 1, 2, and 3, you can give them all as positional arguments. But if you want to do 1, 2, and 4, you have to do 1, 2, and then you can give the 4th, but the 4th can only be given as a keyword argument, right? Because if you give it as a positional argument, it'll be interpreted as the 3rd argument, right? which is slightly more specific than what they've said, though in effect it's the same thing. Def bad function n equals 5, word counter, return none. Okay, dictionary subtraction. Suppose we want to spell check a book. That is, find a list of words that might be misspelled. One way to do that is to find words in the book that don't appear in a list of valid words. In previous chapters, we've used a list of words that are considered valid in word games like Scrabble. Now we'll use this list to spell check Robert Louis Stevenson. You can think of this problem as set subtraction. Yeah. Want to find all the words from the set. Okay. Yeah. As we've done before, we can read the contents of words.txt and split into a list of strings. Done. We've gotten all the valid words. Subtract. Now to identify words that appear in the book but not in the word list, we'll use subtract, which takes two dictionaries as parameters and returns a new dictionary that contains all the keys from one that are not in the other. Res key equals D1 key. Okay. For some reason I thought this was like some sort of unique operator. It's just literally a function that does that for you. So basically res is the new dict that's initialized as an empty dict for key in D1 for every key in D1. If that key is not present in D2, we do res key equals D1 key, right? So anything that's in D1 that's not in D2 gets put into this dict, and that's what we return. All of these are already run. I'm just rerunning everything. So diff equals subtract word counter comma valid words, which gives us diff. And then we can give it to our function from earlier, print most common, to see the difference. I.A. Utterson, Mr. Hyde. The most common misspelled words are mostly names and a few single letter words. Mr. Utterson, Dr. Jekyll's friend and lawyer. If we select words that only appear once, they are more likely to be actual misspellings. We can do that by looping through the items and making a list of words with frequency 1. I'm just going to pause this for a second. Sorry about that. I just thought up of a thing that I wanted to log. Most common misspelled words are mostly names and a few single letter words. Blah, blah, blah. If we select words that only appear once, they are more likely to be actual misspellings. We can do that by looping through the items and making a list of words with frequency 1. For word, comma, freak and diff.items, if freak equals 1, singletons.append word. Here are the last few elements of this list. Gesticulated, abjection, circumscription, re-indue, fear-struck. Most of them are valid words that are not in the word list, but re-indue appears to be a misspelling of re-induce, so at least we found one legitimate error. So one thing I'll point out, up till this point, we haven't done... Like, analysis is a fancy word, and this technically is an analysis, but I do want to point out that what they've outlined here in this chapter, it's kind of important to grasp, not just for computer science, but also for data science, but also for life, right? Like, think about all the ways to check something, right? We don't do this as a society anymore, at least not the mere mortals, right? Didn't used to be the case. I think people used to be more keyed in to what is actually happening, and so would analyze it internally in their head differently. And it's weird, like, for people who engage in it in this day and age are super analytics. Like, they can take any piece of information and really drill down into the truth of the matter from any news article or whatever. And then there's people who are like, oh, I read this, it's true, right? And unfortunately, that second one is a lot more common. And confirming the veracity of things is important, right? Because, for example, you wanted to say you read a word in this book, right? And you're like, oh, this word's misspelled. Is it really misspelled, or did you just not know that word, right? It's a simple concept of taking the time to affirm the veracity of anything and everything, honestly. And this thing lines up a good structured way to think about how you would do that, right? Um, yeah. So, anyways, because this kind of structure could be applied to almost anything, like if you were to think about it, right? So we have a book, right? And we want to check it for misspellings because we believe there's misspellings in there, right? What did we do? We got all the words from the book, makes sense. We made sure to toss out any funky stuff that is valid but would like can easily be construed as invalid, right? We found and uh, found and collated a ratified or a verified list, and then we checked it against that list, right? And even then, we still used our critical mind, right? We didn't think like, oh, all of these words are misspellings that our process sped out. We went and like, okay, we didn't do it in this, but if you were really doing this and you didn't know any of these words that showed up, these words, you'd go look them up, right? Um, Now let's reframe the question. What if it's a news article? Okay, it's a news article, and you don't think it's true, right? Let's say that. What do you do? Well, first you read the actual news article. Second, if you either find um, a source of truth that is deeper than that article, or try to find multiple sources of truth, one or the other, right? The first is better. The second is more common because it's easier to do, and in some cases the only option. Um, you compare your ground truth, or as close to ground truth as you can really get, with what is being presented to you. You analyze the differences to see what is editorial fluff versus what someone says as fact. And then you actually are able to say, okay, this is a fact and this is not. Right? So that's extremely important. That's extremely important. That's extremely important outside of computer science, in my opinion. Random. I think we haven't had one of these random asides in a while, so a long time coming. Random numbers. As a step towards Markov generation, next we'll choose a random sequence of words from word counter. But first, let's talk about randomness. Given the same inputs, most computer programs are deterministic, which means they generate the same outputs every time. Determinism is usually a good thing since we can expect the same calculation to yield the same result. For some applications, though, we want the computer to be unpredictable. Games are one example, but there are more. Yeah, like machine learning. Making a program truly non-deterministic turns out to be difficult, but there are ways to fake it. One is to use algorithms that generate pseudo-random numbers. Pseudo-random numbers are not truly random because they are generated by a deterministic computation, but just by looking at the numbers, it is all but impossible to distinguish them from random. The random module provides functions that generate pseudo-random numbers, which I will simply call random from here on. We can import it like this. Import random, random.seed. So, yeah, so essentially randomness in comp sci doesn't exactly exist. What we do is we have algorithms that simulate randomness, right? So if you've ever had like a coin flip in a game, or like the Google coin flip thing, it is essentially random for us, but it's only random because there's actually a literal algorithm that keeps track of its current state, keeps track of its previous states to make sure that the next outcome actually fits reasonably well within a statistical distribution. Um, which is not the same as truly random, right? If I told you to pick a number, any number, that would be random, right? You just pick a random number. In fact, technically, that's not truly random either, because most people are limited to like a certain range of numbers. Like very few people would be 1 quintillion, 591 trillion, 325 billion, blah 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 blah. Like most people are not going to think that. So even that is not truly random in terms of the statistical scale of numbers, but still, that's random, right? That's like just you just decided something, right? Um, I can make many more statements like this, but you get the point. And so, what a seed is essentially a way to pin how the numbers are generated. So, if you don't set a seed, the random module will initialize its own random number generator by generating a seed, right? And I don't exactly know how they do this. My guess is that some utilization of the Unix timestamp, which is a constantly increasing integer, essentially, or something like that, is used with some sort of mixture of things to create a seed. But if you don't do that, and if you actually set the seed yourself, what happens is that all calls to the random module or anywhere where randomness is used in your program from these random modules or other algorithms and things like that that actually utilize the feature, they will always produce the same numbers, right? Which may not be good in certain situations, right? Like if you're truly looking for randomness, but it is extremely helpful when you're developing. Because when you're developing, you want to know how things are working, right? You want to have a predictable set of outcomes. And once everything's put together, then you just let it off the leash and you take off the seed, right? And even then, maybe not necessarily so, because in machine learning, for example, if you want an experiment to be reproducible and publishable, well, you need to set seed, right? Because if you don't, then someone else who takes it and runs your code is like, no, I didn't get even close to the same results you did. Why, right? Sometimes the random number generator screwed you, right? So set the seed. Anyways, random module provides a function called choice that chooses an element from a list at random, with every element having the same probability of being chosen. Random.choice t equals 1, 2, 3, random.choice 1. If you call the function again, you might get the same element again or a different one. In the long run, we expect to get every element about the same number of times. If you use choice with the dictionary, you get a key error. Yeah, so this only works with lists. To choose a random key, you have to put the keys in a list and then call choice. So words, list, word counter, random.choice. Words. If we generate a random sequence of words, it doesn't make much sense. Well, duh. Part of the problem is that we're not taking into account that some words are more common than others. The results will be better if we choose words with different weights, so that some are chosen more often than others. If you use the values from word counter as weights, each word is chosen with a probability that depends on its frequency. So weights equals word counter dot values. This is a lot of ML stuff. I'm surprised. This is it's cool stuff, but it's not stuff that I think is there in most CS primers, or at least it didn't used to be when I was young. I guess ML and all this stuff is really starting to pick up, so more and more people want something regarding this in their books, so maybe that's why. Sorry, the AC was starting to get cold, so I just wanted to turn that off. But yeah, so the term weights is borrowed from machine learning, and it's exactly what this is describing, right? Essentially, is like if you have some outcome that shouldn't be completely equivalent across others, you can weight that outcome, right? The random module provides another function called choices that takes weights as an optional argument. So you can give random.choices words comma weights dan, and takes another optional argument k that specifies the number of words to select. K equals 6. Random words, reach streets, disappearance, a said 2. The result is a list of strings that can join into something that looks more like a sentence. Reach streets, disappearance, a said 2. Yeah, definitely not a good one. If you choose words from the book at random, you get a sense of the vocabulary, but a series of random words seldom makes sense because there is no relationship between successive words. For example, in a real sentence, you expect an article like the to be followed by an adjective or a noun, and probably not a verb or an adverb. So the next step is to look at these relationships between words. Yeah, so bigrams. This is totally classic NLP. Instead of looking at one word at a time, we'll look at a sequence of two words, which are called bigrams, a sequence of three words, which is a trigram, and a sequence of some unspecified number of words, which is called an n-gram. Let's write a program that finds all the bigrams in the book and the number of times each one appears. To store the results, we'll use a dictionary where the keys are tuples of strings that represent bigrams and the values are integers that represent frequencies. That's called a bigram counter. So it's going to be very similar to the previous loop we wrote about going through the entire book and just getting each unique word. It's just going to be, instead of each word, it's going to be like each word and you get the next word too, and that'll be the key. And then you go to the second word, which is technically as part of the first key, and then you take that word and the next word, and it's essentially going to be that loop. That's what they're going to build to. And you can expand the same logic to as many grams as you want. You want some grams? You want a gram? Give me a gram. No, I'm not a drug dealer, I swear. Or am I? Okay, I'm just having fun with this now. Following function takes a list of two strings as a parameter. First, it makes a tuple of two strings, which can be used as a key in the dictionary. Then it adds the key to bigram counter if it doesn't exist, or increments the frequency as it does. So key equals tuple bigram. If key not in bigram counter key equals 1, else bigram counter key plus equals 1. As we go through the book, we have to keep track of each pair of consecutive verbs. So if we see the sequence man is not truly one, we would add the bigrams man is not truly, and so on, as I described. To keep track of these bigrams, we'll use a list called window because it's like a window that slides over the pages of the book, showing only two words at a time. Initially, window is empty. We'll use the following function to process the words one at a time. Def process word window.append word. If len window equals 2, count bigram window.pop 0. The first time this function is called, it appends the given word to window. Since there is only one word in the window, we don't have a bigram yet, so the function ends. The second time it's called, and every time thereafter, it appends a second word to window. Since there are two words in the window, it calls count bigram to keep track of how many times each bigram appears. Then it uses pop to remove the first word from the window. The following program loops through the words in the book and processes them one at a time. So process words calls on count bigram. Bigram takes, what does bigram take? A list, yeah, a list, the window, if you will, and just does that. So windows, once again, another DS concept. It's used in multiple types of calculations and functions. It's just like a sliding window, right? So another simple example is like, okay, you can have, for example, if you're a company and you want to talk about average monthly recurring revenue, right? You can calculate that for the entire fiscal year, but also there's a thing as rolling averages, so you'll calculate it for each quarter separately, right? Which is different windows, and then you can have a sliding window where you can calculate it for the first 3 months, then the 3 months after that, then the 3 months after that, right? Which is important to do for just multiple reasons. Yeah. So I believe, yeah. The second time it's called and every time thereafter, blah, blah, blah. And we write a loop that just uses both of the functions, clean word and process word, right? And count bigram. Um, Print most common bigram counter, and then boom, of the, in the, it was, and the, to the. Looking at these results, we can get a sense of which pairs of words are most likely to appear together. We can also use the results to generate random text like this: random.seed0, random bigrams, random choices, bigrams, weights, k equals 6. So this is as earlier. Bigram counter values, list bigram counter. Yeah. So, okay. Bigrams here in this case is just taking all the keys from bigram counter. Weights equals bigram counter values. Got it. Because remember, the keys are the actual bigrams and the values are their occurrence, their frequency. Random bigrams, random dot choices, bigrams, weights equals weights, k equals 6. Easy. 4 pair in random bigrams, print blah. To suggest this preface to detain fact is above all the laboratory. Okay, that's actually like, I mean, it doesn't make any sense, right? But it's a hell of a lot better than totally random words or words that on their own are statistically accurate. So this is a small sidebar into NLP. This is kind of the big thing, right? And this was like bigrams or trigrams, just n-grams, and like the bag of. So before this, what we did, where we just took the words, that's the bag of words model. And then we moved from the bag of words model in NLP to the bag of n-grams model, which is what we're doing right now. I guess this gets into Markov analysis, right? And then there's TF-IDF, which is term frequency, inverse document frequency. Basically, everything in NLP all the way up till now, even with transformers, what we do with LLMs, which is amazing, is figuring out how to algorithmically, or more importantly, numerically represent context in natural language, right? Which is funny because if you read more about transformers, like that's like kind of the whole thing as to why transformers have taken over the world, is because they're actually extremely good at keeping that context. I think the groundbreaking paper was "Attention is all you need." Attention is all. Yeah, I think this is where BERT. When did this come out? 2017. Best performing models. We propose a new simple transformer based solely on attention dispensing with current. Yeah, so I believe this was the original. Yeah, this was the original. I think this might have even led to the release of BERT. I'm not sure. Let's see. Demos, related papers. What are influence flowers? I'm just going on a bit of a tangent here. Influence flower visualizes. Whoa. Okay. That's gorgeous. Anyways. Sorry about that. Getting back to this. Anyways, continuing on, bigrams, a list of okay, so we just go through the bigrams, we get this. So we have generating text is better than choosing random words, but still doesn't make a lot of sense. Very true. Markov analysis. We can do better with Markov chain text analysis, which computes for each word in a text the list of words that come next. As an example, we analyze these lyrics from Monty Python's song Eric the Have to Be. To store the results, we'll use a dictionary that maps for from each word to the list of words that follow it. Oh, so Markov chains is essentially n-grams through till the end. As an example, let's start with the first two words of the song. First equals half, second equals hey. This first word is not in successor map. We have to add a new item that maps from the first word to add a list containing the second word. If the first word is not in successor map, okay, so successor map, first half, second first word, then we give second word, successor map A. The first word is already in the dictionary. We can look it up to get the list of successors. Half a not. We can look it up to get the list of successors we've seen so far and append a new one. I think these are just examples. Successor map first dot append second. The following function encapsulates these steps. If first not in the first successor map first dot append second. Yeah, so basically if it doesn't exist, add it, and if it does exist, append it to the list that begins with it. If the same bigram appears more than once, the second word is added to the list more than once. In this way, successor map keeps track of how many times each successor appears. As we did in this previous section, we'll use a list called window to store pairs of consecutive words, and we'll use the following function to process. Oh, so we're still doing bigrams, okay. I thought it was like literally all the words, but this is basically the way we did previously is just all bigrams, and this is more like all potential bigrams. I actually don't know much about how Markov analysis works. I know it's like important stuff, but I don't know that much. I know it exists, that's about it. Same bigram appears more than once, second word is added to the list more than once. In this way, successor map keeps track of how many times each successor appears. As we did in the previous section, we'll use a list called window to store pairs of consecutive words, and we'll use the following function to process the words one at a time. So half and half not, okay. I just want to confirm that half and half not were both actually valid bigrams from this, and it is. There's also half the. Anyway. So process word bigram, and then we build a successor map with this, and here are the results: half not, half the, be, viz, be philosophically, be has, philosophically must. The word half can be followed by not, or the. The word a can be followed by be or viz. Most of the other words appear only once, so they're only followed by a single word. Man, this is a longer chapter and a longer video. I'm happy about this. I am actually, because the last few videos were getting a little boring. I'm gonna charge me the laptop up real quick. Now let's analyze the book. So now we do the same thing except the whole book, and we get like a giant pair over here. For key value and successor map items, if len value equals 7 and has duplicates value, print key value. So yeah. So once we've done this, we can look this up, and basically what he's done is he's checked for ones with value 7. I don't understand value 7. Oh, if len value, no, okay, sorry, that makes more sense. If len value equals 7, so if there's 7 or more options, so if there is 7 options, not 7 or more, 7, because this is equals, should be greater than equals. Is it like ridiculous if it's greater than equals? Oh yeah, it's way ridiculous. Okay, so we're gonna switch that back, right? And also has duplicates. So this lists all of the bigram options. So story is followed by off multiple times, or indeed but, story 4, officials. Yeah, this is actually 3 times. Successor map going east, going in, going to, 2 up, 2 off. In this list of successors, notice that the word to appears 3 times. The other successors only appear once. Generating text. Word Aldo. Successors equals successor map word successors. So basically, you're just going to do a random choice on the successors. Right? Yeah, there you go, word I. The same word appears more than once in the list is more likely to be selected. Repeating these steps, we can use the following loop to generate a longer series. Of a slight chance be preferred to communicate the good. Let's try again. Of temptation of evening and forever despised and then after. I swear to God, these are just some random ass IQs. The lawyer good-naturedly the semblance of some resemblance to be. Okay. The result sounds more like a real sentence, but it still doesn't make much sense. We can do better using more than one word as a key in a successor map. For example, we can make a dictionary that maps from each bigram or trigram to the list of words that come next. As an exercise, you will have a chance to implement this analysis and see what the results look like. I'm sure that's in the exercises, and yeah, that's a fun one. It's a fun one. This one I personally like because the other ones are also fun, honestly, and they're also tough. I think this one's going to be tougher because it's using some concepts that actually aren't, like, I think should be part of. I don't think they should be part of this book. I think it's useful that they are because I feel like a lot of people come to Python because of data science. But yeah. Anyways, debugging. At this point, we're writing more substantial programs, and you might find that you're spending more time debugging. If you're stuck on a difficult bug, here are a few things to try. Reading. Examine your code, read it back to yourself, and check what it says. Check that it says what you meant to say. Running. Experiment by making changes and running different versions. Often, if you display the right thing at the right place in the program, the problem becomes obvious. But sometimes you have to build scaffolding. Ruminating, taking some time to think. What kind of error is it? Syntax, runtime, semantic. What information can you get from the rubber ducking? If you explain the problem to someone else, you sometimes find the answer before you finish asking the question. Often, you don't need the person. You could just talk to a rubber duck. And that's the origin of the well-known strategy called rubber duck debugging. Yeah. He is not making this up. It is true. He didn't even need the link. I knew that already. Retreating. At some point, the best thing to do is back up, undoing recent changes until you get a program that works. Then you can start rebuilding. Resting. If you give your brain a break. Okay, so just good tips. Beginning programmers sometimes get stuck on one of these activities and forget the others. Each activity comes with its own failure mode. For example, reading your code works if the problem is a typographical error, but not if the problem is a conceptual misunderstanding. If you don't understand what your program does, you can read it 100 times and never see the error because the error is in your head. Running experiments can work, especially if you run small, simple tests, but if you run experiments without thinking or reading the code, it can take a long time to figure out what's happening. You have to take time to think. Debugging is like an experimental science. You should have at least one hypothesis about what the problem is. If there are 2 or more possibilities, try to think of a test that would eliminate one of them. But even the best debugging techniques will fail if there are too many errors, or if the code you are trying to fix is too big and complicated. Sometimes the best option is to retreat, simplifying the program until you get back to something that works. Beginning programmers are often reluctant to retreat because they can't stand to delete a line of code even if it's wrong. If it makes you feel better, copy your program into another file before you start stripping down, then you can copy the pieces back one at a time. Or I just commented it out. I'm like, I don't want to toss this right now because I could reuse this maybe. Let me finish with this feature and then maybe I'll toss it, maybe I won't. I don't know. That's what I ended up doing. But yeah, definitely all of these things are true. I think a lot of these things are good for anything. Like I actually like these debugging blurbs, especially because if you think about them outside of the context of computer science, they're still very applicable, right? Default value. So this is the glossary. Exercises. In add bigram, this creates a new list or appends an element 26 depending on whether the key is already in the dictionary. Dictionaries provide a method called setDefault that we can use to do the same thing more concisely. Ask, what is setDefault do? SetDefault method returns the value of the item with the specified key. If the key does not exist, insert the key with the specified value. See example below. Yeah, okay, fair enough. Just chapter Markov chain text analysis generation. If you're curious, you can ask Virtual for more information on the topic. One of the things you might learn is that virtual instances use algorithms that are similar in many ways, but also different in importance. Ask if what are the differences in a large language model like GPT and Markov chain? A lot. Exercise. Write a function that counts the number of times each trigram sequence of 3 words appears if your test function. I am, once again, not going to do this, but I am very tempted to do this. I am super duper tempted to do this, but I am, unlike prior options, trying to stay on target. And I still believe that the best way to learn is to learn more than you need to learn. But also orient yourself at the same time right now. And I am oriented, and I'm mostly doing this for someone else. So I do just want to rush through it, gain an awareness of it, so that as they're going through it, I'm not like, what? On anything. Which is good if you're ever actually helping someone out or trying to help them out. Like, go through it with them. Don't pretend like you know everything. You can use the following loop to test your functional lyrics. Eric, the half a B. Successor map. You can use the following loop to test your function with the words from the book. Blah, blah, blah. Okay, so great exercises. Definitely recommend. This was a good video. It was a fun chapter, actually. I really liked it. It was very enjoyable. I'm actually curious about the next one as well, because files I get how to work with, but based on how much detail they go into this chapter, that would be helpful for me, because I do need to be working with Postgres and such pretty soon, though highly doubt they're going to be talking about Postgres here, telling me how to use Postgres. That's it for me. Thank you everyone for watching, and I'll catch you in the next video. Bye-bye.